In this video and the next few videos, we are going to study the Rust concurrency libraries. The key point of this library is that the implementations are potentially unsafe because the Rust type system cannot analyze the safety of those implementations. But they are enveloped within Safe API, which means that the user of the API doesn't need to take into account the implementations at all. The API is correct, and every possible uses of such API will not incur undefined behavior or any kind of unsafe behaviors. So this is the key abstraction that is provided by Rust, and we are going to study such libraries in the next few videos. Okay, so the key point, as I said, is the user don't need to worry about the safety at all. They just can use the API without worrying about the safety. The famous libraries include those inside STD, which is the standard library of Rust, and what is called parking lot, which provides the low-level concurrency features like mutexes or conditional variables, and those inside these courses repository, and they include the spin log or sequence log that is widely used in the low-level concurrency, and the crossbeam, which provides many things, including the scope thread, which will deal with the difficulties or challenges that is imposed in the standard library thread library. And also, we are going to study what is called cache padded, that is for defeating what is called fault sharing. And we are going to study channel, that is also used in the skeleton code for homework 1. The channel is basically a queue where you can send data and you can receive data. So this is a channel, and that is provided by Crossbeam with a Safe API. We are also going to study Rayon, which is a parallelism library on top of Crossbeam and other things. And the prominent feature of this Rayon is into per iter, that is converting, for example, a vector, a list of elements, into a parallel iterator, so that if you are just sending a function to this iterator, then the function is automatically parallelly executed for each element in the vector. So it can be done without any worrying about the concurrencies or parallelism. As far as you can call this into per iter and then run some function, then it is automatically and well parallelized. So this is the higher level API than Crossbeam and other concurrency libraries. And in this course, we are going to study the API of those Rayon. So let me start with the standard library. So here is an example of a standard library's features. As you can see, there are a few imports of the standard library features, including reference counter, atomic reference counter, or a thread, and just a single thread reference counter, and slip function that slips a thread, that puts the current thread into sleep for a predefined duration. And yeah, that's all. So in this program, let's assume that we have the value 5 that is named 5, and we want to share this value among multiple threads. And that's the reason why we spawn multiple threads here. And for 10 times, we are spawning a thread 10 times. First, we are going to put this value 5 into atomic reference counter so that it can be shared among multiple threads. So usually, a data alone cannot be shared among multiple threads. If you want to share a value among multiple threads, you need to put them into atomic reference counter. This atomic reference counter means that you have a counter for this value. So as far as you have a pointer, a reference counted pointer, then it is guaranteed that the underlying value will not be destructed. So as far as you have 5 here, that is a counter, then the value is live. It is proven by the API. Okay, so we are cloning the reference counter that is effectively increasing the reference counting number. So here, when the 5 is declared, the reference counter is 1 because there is only one reference to this 5. And in this for iteration, the 5 is cloned. As a result, the reference counter is incremented from 1 to 2. And this 5 is the holder of this another count for this underlying value. And this 5 is then transferred into a new thread. A new thread is spawned with this API, and in the new thread, this function is executed. This is a notation for a function. This is also called a closure in programming languages theory. And this function is newly created, and this function is given no argument. It is quite expected because we cannot, in this API, we cannot send an argument to the new function. We just spawn a new thread with the function, and that function should not be given any argument. Also, but the fact that this 5 is transferred from the enclosing function into this function. So it is not sent via argument or parameter. It is just sent as a reference. So this move means that, oh, there was 5, the variable 5, and it is used here as well. And as a result, this value here, variable here, should be transferred or moved into the another thread. So 5 is moved to another thread. That's the meaning of this move. That effectively means that before execution of this thread spawn, the owner of this reference counter is the main thread. The main thread has a 5 variable, and this variable holds the reference counter for the underlying value. But when it is moved into this enclosed function, the reference counter is being transferred into this thread, and especially this variable 5 is holding the reference counter. And when the thread is ended and the scope is ended, the variable 5 is no longer used, and as a result, the destructor for this variable 5 is called, and in the destructor of this 5, which is an atomic reference counter, the reference counter is decremented by 1. So overall, in an iteration of this for statement, reference counter is incremented and it is moved into the new thread. And at the end of the new thread, the atomic reference counter is decremented. And as a result, at this point of time, when all threads are executed and finished, only the reference counter for this variable 5 becomes 1. It is incremented to 11, which is 1 plus 10, and then decremented 10 times. And as a result, its final value is 1. Okay, so after waiting for all the threads, all 10 threads to finish, here we are just waiting for 1 second, but there is a better way to wait for another thread. But let's wait for just 1 second so that all threads are finished beforehand. The reference counter is 1, and at the end of this main function, the 5 is also destructed or dropped. And as a result, each reference counter is decremented from 1 to 0, and the underlying value is also dropped. So this is basically the internal working of this program. So overall, the moral of the story is that there's an underlying data that is shared among multiple threads, which is 5. And this data 5 is cloned and then moved to the thread, and it is executing some function, and then the reference counter is dropped. And at the end of the day, when all threads are executed and the main thread is finished, all the references are gone, and as a result, the underlying value 5 is dropped. So when you execute this, you can see that each thread is executing its own printf function, and as a result, 10 files are printed in this code. So that is basically what's going on inside this code. So let's see the API of those the things are presented in this code. The first thing to see is thread spawn. This is a spawn. You are giving this function a closure or a function here, fn here. F is a function that is given nothing, and it returns a value of type t. T is a type parameter. It can be anything. So it is just a function. And as a result, it is returning what is called join handle. And this join handle is used to join the thread. So instead of waiting for 1 second, for example, you can create a thread and get the join handle, and you can join it. So it is a more traditional way for waiting for a thread to finish. So if you are going to, so this will be also used in the homework 1, because you need to implement what is called a thread pool. And in the implementation of a thread pool, you need to wait for all the handlers to be, all the threads to be joined at the end of the execution. So, okay, so far so good. It is a standard library function, thread spawn, and this just creates a new thread. And the function f is executed. And the return value is t, and when the thread is joined like this, then the return value will be the value t. So it is basically the internal working, API of this. And you can see that this function is marked as safe. The meaning of this is that you can arbitrarily call this spawn function, and you don't need to worry about the safety of this function call because it is safe, as marked as Rust standard library. And even though you've spawned, for example, 100 times of this function, and it'll be okay. As far as the function is marked as safe, then you can do anything with this API. That's the guarantee that is provided by Rust. Compare this with the C or C++ API. For example, if you pass the null pointer as the function closure in the C or C++ API, and then the behavior will be undefined. And as a result, you need to deal with such an error case on your own. But when using a Rust API, you don't need to worry about that because this type, fn1's, the trait fn1's guarantees that the function that is given to the spawn is satisfying a certain requirement. And one of the requirements is that it is a function that can be called at least once. And it is given no values, no arguments basically, and returns a value t. It is the information that contract is described in this function signature. And that's the reason why we don't need to worry about the safety of this function. Okay, so here, this is a way to create a function that implements fn1s on the fly, basically. You don't need to create a function outside of this fn function here. You can just create a function inlined in this line. So this is what is called closure in the programming language theory, which is also deployed in most modern programming languages, including C++. And just you can execute that function here. Okay, so far so good. And I'd like to see the arc here. So here is an example arc, atomic reference counter. So we already saw a similar example to those in the Rust playground. So it is a little bit more involved, but basically they do the same thing. It is creating 10 threads, and for each thread, a reference counted pointer to the underlying value is passed, and then it is printed. So the main idea is the same. The main idea of this reference counter is that it is a reference counting pointer that can be safely shared among the thread. I mean, safely sent to another thread. So that is what is meant by this thread safe. Atomic reference counter can be arbitrarily sent to any thread. So that is the meaning of this thread safety here. So in this example, the reference counter to the underlying value is another thread. So that's the reason why we use atomic reference counter arc. Okay, then now let me explain a little bit more about the constraint that is imposed on the thread spawn function. Okay, this requirement is quite straightforward. F should be a function that is returning t. So far so good. But what is required additionally is that the f function it should be send and it should be static scoped. Furthermore, the return value t is also send and it is statically scoped. So let me explain what the meaning of this with an example. Send and static scoped. Let me show you an example of this example here. Okay, instead of wrapping the value inside a reference counter, we want to wrap a value with a single thread reference counter. RC is also provided by the standard library, and let's say it is it's a single-threaded reference counter, and it will be a better example here. And let's run it, and it is going to say, oh, this RC cannot be sent between threads safely. So it basically means that RC doesn't implement the thread send. So that's the reason why this 5 cannot move into this closure. So since 5 is moved into this closure, the closure itself, the function itself, cannot be sent. So that's the reason why this is rejecting the compilation of this, because the f must be implementing the send trait. So let me explain why ROS requires that. So 5 is the implementation of reference counter assumes that the increment and decrement are not concurrent at all. So when you increment or decrement a reference counter for this RC, then it should be the case that that is the only thread that is incrementing or decrementing the reference counter. However, in this program, if it would be compiled, it is not the case. The reason is that at the end of the thread's execution, the 5 is dropped, and as a result, reference counter will be decremented. But this decrement can be executed by multiple threads, say 10 threads at the same time, because they are all executed in parallel. So that's the reason why this RC cannot be used for this example, because the decrement is not meant to be run concurrently. So that's the reason why the RC here is not marked as send. This reference counted pointer cannot be sent to another thread. That's the meaning of the fact that RC is not marked as send. On the other hand, ARC, which is atomic reference counter, it takes into account the possibilities that the increment and decrement can be executed at the same time, concurrently by multiple threads. So that's the reason why atomic reference counters are marked as a send, and they can be sent to another thread. So recall that when this 5 was ARC, then it is just safely executed. But on the other end, if this 5 is a single thread reference counter, the ROS compiler rejects this program by saying that, oh, RC cannot be sent between threads safely. So as a result, I am I am bailing out this compilation. RC is not marked as send, but F is marked as send. So they are some mismatches. So I fail to compile it, and I just give up in compiling this. So that's the meaning of this send here. All the closure should be safe to send to another thread because it will be executed in another thread. Similarly, the return type should also be implementing send because the return value should be sent from a thread to another thread. So if it is executed in the spawn thread, then the the thread that spawned this thread, which I will call spawner will have the join handle, and it will eventually get the return value. So that's the reason why this T should be sent from the spawn thread to the spawner. So that's the reason why T should also be sent. Okay, so far so good. And I'd like to explain the meaning of the static scope now. Now, let me change the example a little bit. In this example, there is a 5, and 5, the reference to the value 5 is taken, and the 5 is now a reference to the value 5 that is declared here. And the reference is moved to this spawn thread, and it is referenced. So it looks like safe, but actually it is not, because when this slip is not there, it may be possible that the main thread may exit before the spawn thread. Because there is no order between the execution of those threads. That's the reason why the main thread can be finished before the spawn thread. If that happens, then the 5 declared here is dropped here. It can be dropped and destructed before the execution of another thread. And as a result, this 5 can be a dangling pointer to the stack. That was valid, but now invalid because the main function returned. And as a result, this print function is very much unsafe because it is referencing a dangling pointer. It should not happen in the safe part of the Rust. That's the reason why the spawn function requires that the f here, the function closure, and the return value are statically scoped. That means that the value should be valid for the entire execution. The static scope means that it should be valid from the beginning of the execution of the program until the end of the execution of the program. It should be valid for the entire execution of the program. That's the meaning of the static scope. Here, 5 is not the static scope because 5 is constructed after the execution, the invocation of the main function, and it is dropped or destructed before the end of the invocation of the main function. So its scope is from the line number 7 to line number 23, and it is not guaranteed to leave when this thread function is executed. It is well before the execution of this print function that the 5 variable is destructed or dropped. So that's the reason why we should reject this program. It is very much okay or even desirable to reject this program because 5 is not guaranteed to be alive at this line. So let's see what it says. Rust says that 5 does not live long enough because it should be static as required by the API of the thread spawn, but it is dropped here, which may be before the 5 is used here. That's the reason why I'm going to bail out this compilation, and it is safe to do so. It is desirable to do so because it is actually a buggy. So that's the meaning of the static scope here. in addition to requiring that the closures and the return value are sent, which means that they can be sent to another thread, they also should be static. That means that the value that is inside the closures and the return value should be live for the entire execution. So that's the meaning of this requirement. So as far as these three conditions are met, it is guaranteed by the Rust library that the spawn function is very much okay. It does not incur any kind of unsafe behaviors, including dangling pointers or undefined behaviors or other very scary things. It is absolutely safe. That is guaranteed by Rust standard library. But interesting fact is that the implementation of this spawn may not be 100% safe. Let's say that inside this spawn function, it is calling what is called spawn unchecked f unsafely, which means that Rust compiler cannot analyze itself that this implementation of this function is 100% safe. But the library author somehow manually inspected this implementation and guarantees by this contract of this function definition, a signature that, oh, it should be safe. Even though Rust compiler doesn't know the safety of this, I know, the library author, knows that this is absolutely safe. That's the reason why I am marking this as safe function instead of unsafe function. So standard library provides a bunch of concurrency features that has safe API, including threads, arc, and some other things. And you can use this and with absolute safety guarantee. And learning this requirement is a good thing. So in general, when you want to spawn a thread, these three things should be satisfied. So it is not only specific to Rust, but also generally applicable to systems programming. In CS++ also, if f is a function pointer, it should be actually a function, and in addition to that, it should not be dealing with some thread local storage, and it should be safely sent to another thread, and it should be statically scoped because we don't know whether the thread is going to unlive the enclosing function or not. So this knowledge itself is not only applicable to Rust, but also applicable to other systems programming languages. What is learned here, what is evident in this Rust API is that this folklore knowledge is somehow codified or somehow explicitly contracted in the Rust API. And if you are well aware of this Rust API, you will have higher chance to write a safe program, not only in Rust, but also in other programming languages. Okay, so far so good. So we learned a few APIs and using this simple program, which prints just 10 fives and in 10 threads. So it is an interesting example that motivates many of the APIs. And Arc has another API rather than new. It has what is called a weak, but the details of this are not covered in this course. So if you're interested, please read this reference and see what's going on there, or with the weak type and other APIs. Also, I believe that you will be interested in thread markers, including send and sync. Send is basically marking that a type is sent to another thread, as I said. Types that can be transferred across thread boundaries. And all concurrency libraries of Rust are developed on top of this marker. So you need to somehow make explicit what is sendable and what is not sendable in concurrent programming. Okay, there are many types are basically sendable. What is interesting is that scope reference are also sendable because we have a scope here, and if if T is sync, which means that it can be accessed by multiple threads, then the reference can be sent to another thread. So the meaning of that is that T sync means that it can be accessed by multiple threads at the same time. So that's the meaning of this sync, which will be dealt here. And if it is the case, then the reference can be arbitrarily sent to another thread because the underlying value T is concurrently accessible in a safe way. So it is basically the meaning of these two implementations. And the other side of the coin is the sync trait, which means that, as I said, sync types are those that it is safe to share references between the threads. So the send and sync are very much related. This is the definition. T is sync if and only if the reference to T is sendable. So this is basically the meaning of the relationship, the formal relationship between send and sync, and that's the reason why this is implemented in this way. If T is sync, then the references are sent. Probably the information is formally represented in this code, and please memorize the meaning of these two. These two lines are worth memorizing for all concurrent programming in Rust, and this formal relationship between the pointers and the pointers and references and the underlying type are also worth memorizing. And when you're going to implement your own concurrency libraries, you should mark what is expected for argument and return values, whether they should be send or whether it should be sync or etc. So that's one of the reasons why you need to understand the concept behind the send and sync traits well. So going back to this point function, the reason why the closure and this return value should be sent is the value should be sent to another thread. And similarly, arc requires that, let's see the new function. Okay. Yeah. So here deref. Okay. So arc somehow requires that the underlying value, underlying type T, should be send and sync. Oh yeah, here. Arc of T will implement send and sync as long as the underlying type T implements send and sync. So that means that if the underlying type can be accessed among multiple threads and it can be sent to another thread, then the arc type is also send and sync, which means that the reference counted pointer can be sent to another thread as far as the underlying value is sync as well. So that's basically the contract that is imposed by this arc type. And please investigate the types of these arc APIs. And as I said, the send and sync will provide a formal contract between the programmer or user of this arc and the implementer of the standard libraries feature. And that means that the T that should be put inside this arc should be send and sync. And indeed, the value integer values are sendable and sync. And it's a reason why this arcnew, the result of this arcnew, which is the 5 here, is also sendable and sync. That's the reason why we can send the 5 value here, and as a result, the entire closure is sendable. It implements send by conforming to the API of this arc. Okay, so far we studied the four members of the standard libraries regarding concurrency, including thread, arc, which is reference counter, and send and sync. And you can see what's going on here, and please read the documentation more carefully so that you are 100% aware of all the APIs, safe APIs.